Hello students, myself Professor Ankur. I welcome all of you to the gate sum session of analog circuits, and we are going to go for sums session 3 of the topic diode. So let's go for the gate sums. So we're having a question here. The question says a DC current of 26 microampere flows through the circuitry shown. The diode in the circuitry is forward bias and it has an ideality factor of 1. At the quiescent point, the diode has a junction capacitance of 0.5 nanofarad. Its neutral region resistances can be neglected. Assume that the room temperature thermal equivalent voltage is 26 millivolt for omega equal to 2 into 10 raised to 6 radian per second. The amplitude of the small signal component of the diode current in microampere correct up to 1 decimal place is. So if you observe the figure carefully, we are having a battery followed by a voltage source, a diode and a resistor. So now it is as good as a diode is given a DC along with AC. And the important point that we need to understand here that the DC current of 26 microampere is flowing through the circuitry and the thermal voltage is given as 26 millivolt and a device capacitance that is for the diode is given as 0.5 nanofarad. So let's go for the solution. So as you see, the IDQ value is given as 26 microampere. This will help us in calculation of your resistance. So for the diode, the forward resistance can be defined as VT by IDQ. Since the value of VT is 26 millivolt and the DC diode current is 26 microampere, the forward resistance will come as a ratio of those two values and will give you 1 kilo ohm. The capacitance of the junction for the device is given as 5 nanofarad. So once we are given the capacitance value, we can definitely calculate the impedance. If you observe the diode is now having two device parameter. One is its resistance and the other is its capacitance. Implies the diode can be replaced by its equivalent. So here on the right hand side, you can see the equivalent where we are having a resistance RD, a capacitor CJ, a resistance R and a supply voltage of Vs. This is basically the AC equivalent circuitry and that's the reason the DC battery is absent. So if I want to calculate the impedance of the capacitor, the impedance of the capacitor is minus Jx. So automatically when I put the value of Xc as 1 by 2 pi Fc with the omega value given, you will get Zc as minus of J 1000 ohm. Now using that you can calculate the Z equivalent, which is basically for the diode. It is RD parallel with ZCJ. So when you substitute the value of RD and minus of Jx in the formula, you will get Z equivalent as 707.106 angle minus 45 ohm. So that is basically the impedance of that section. The current can be given as I, which will be the voltage value divided by the addition of elements, where the first element is a resistor and the second element is an impedance. So that's the reason the value of I will be Vs divided by Z equivalent plus R. We have already calculated the value of Z equivalent and we are having the value of R. So on solving, when you put the value of Vs as 5 millivolt as per the data given, we get I value as 6.4 microampere. This is the magnitude component of the current. Next question. The output voltage VO of the diode circuitry shown in the figure is connected to an averaging DC voltmeter. The reading of the DC voltmeter in volts, neglecting the voltage drop across the diode is. So if you observe the question carefully, this is from the GATE 2007 ECE paper and we are having a voltage source of 10 sine omega t with a frequency of 50 Hz. Now, since we are having a drop across diode which can be neglected and the circuitry figure is analogous to your half-wave rectifier, the output of the half-wave rectifier will retain only a positive cycle of the AC input and the negative cycle will get clipped off. So once you get only one cycle of the AC input and the other cycle gets clipped off, the output is basically like a fluctuating DC. But when you see a DC averaging voltmeter, it will always measure the average value or the DC value or the DC component or the DC content of that signal at the output side. So we have already a formula measured with respect to the average DC value of a half-wave rectifier. The average DC value of a half-wave rectifier is defined as Vm by pi, where Vm is the peak value of the signal. So with that logic, we can directly find the value as Vm by pi. So the Vm by pi value will give you 3.183 volts. So this is the solution. Next question. GATE 2007 ECE paper. And the question says, in the figure, diode D1 is a real silicon PN junction diode with a drop of 0.7 volts under forward bias condition, and D2 is a Zener diode with a breakdown voltage of minus 6.8 volt. The input Vin of T is periodic square wave of period T, whose one period is shown in the figure. The maximum and the minimum value of the output waveform is. So when you look at the figure carefully, you can see that the input is in the form of a square wave and the circuitry is having a capacitor, diode, a Zener diode, a resistor and the output point. This circuitry is basically like a clamper circuitry. So if it is a clamper circuitry, we need to find what will happen for positive half cycle as well as negative half cycle. So let's go for the solution. So during the positive half cycle, the diode D is going to be forward bias and the Zener is going to be reverse bias. And because of this, I can apply the KVL to the loop where Vin minus Vc minus Vd minus Vz is equal to 0. So automatically you will get the value of Vc as 6.5 volt. That is by substituting the value of input as 14, the drop across diode as 0.7 and the Zener voltage for reverse bias will be giving you 6.8. So solving you will get 6.5. So this is the voltage implies the capacitor will charge to a value of 6.5 volt. And at that point, for the positive half cycle of the input, the output voltage will be the drop across the diode D1 and the Zener reverse voltage D2. So automatically it will be 0.7 and 6.8 addition giving you 7.5 volt. Now when we check the operation in the negative half cycle, in the negative half cycle, your D1 will be reverse bias. So automatically what we have as voltage of the capacitor and voltage of the input giving you an addition effect to generate an output. And when I apply KVL, you will get Vin minus Vc minus Vo is equal to 0. You will get Vo as Vin minus Vc. So the Vin value is minus 14. Substituting it, you will get minus 20.5. So automatically you can see the option A is the correct option. So GATE 2013 ECE paper, this is a 1-mark question. The question says, a voltage of 1000 sine omega t volts is applied between, or you can say across points X and Y and Z. A voltage of 1000 sine omega t volt is applied across Y and Z. Assume diodes are ideal. The voltage measured across W and X in volts is. So now if you observe carefully, the 4 diodes are as good as they are forming the arms of a Winstone's network. We need to check which is the correct option. We are given 4 options for this question. Option A is sine of omega t. Option B is sine of omega t plus magnitude of sine of omega t, the addition effect divided by 2. Option C, the subtraction of the 2 elements sine omega t and magnitude of sine omega t divided by 2. And option D, it is 0 for all t. So to understand what is happening with this circuitry, we need to re-learn the circuitry. And as I have said, that the four diodes are looking as if they are as the arm of the Winstone's network. So rearranging them in the form of the Winstone's network. So here if you observe, you can clearly see there are four diodes 1, 2, 3, 4 with the nodes Y and Z where a voltage source is connected, and X and W across which you are going to have a load of 1 kilo ohm and you're going to measure the output. So now what will happen? Let's go for the solution. So during the positive half cycle of the AC input, all the diodes will be reverse bias and in the off state. So since all the diodes are in the reverse bias, because when I check the positive half cycle with top polarity of the source as plus and the bottom polarity of the source as minus, for the top diodes D1 and D4, the cathode is positive. And for the bottom diode D2 and D3, the anode is basically negative. So overall for all four diodes, the condition is favorable for reverse biasing. That's the reason they will work like open circuit. Automatically the value of I will be 0. Now when I consider the negative half cycle, in the negative half cycle, you will find that point X and point W will become equipotential. And because of this, the value of VO will go to 0. So automatically, when I try to get the value of voltage measured between points W and X in volts, it will remain 0 always for the positive half cycle as well as the negative half cycle. So eventually, the final answer is answer D, which is 0 for all time T.